Okay, so we're talking about stats, and moments ago we talked about some vocabulary terms and the overview, what to expect. In this module, we will be doing Monte Carlo simulations. That's named after Monte Carlo. It's like Vegas, right? Vegas of Europe. The simulations we will be doing, we will use Numpy and Pandas in this Viz library, which you can grab the code for underneath Viz module. And I'm going to set a random seed here so that if you are running the same code in the same order, your random numbers will have that same determinism, at least in the same order. The integer you put here doesn't matter. Just don't put your social or something like that. To generate some random numbers, we're going to be using the Numpy library. Specifically, there is a module inside of Numpy called random. And since there's so much randomness in Numpy, we have not just one random method, .random, we have .choice. So we can produce a list of options. This curriculum is ds.codeup.com. It's a one-to-one the simulations lesson. Okay. .uniform generates a uniform distribution, and that's a mathematician's way of saying a fair coin or a fair die is uniform. Random generates a random float between 0 and 1. Rand_n generates random numbers with a normal distribution, and .normal, if you can believe it, generates a normal distribution with a specified mean and a specified standard deviation. Sometimes you might be given a mean and a standard deviation to tell you about a population. And so we can generate some actual numbers in memory this way. So let's get into our first setup here. Like many probability setups, we're going to start doing things with coins and dice, but then we're going to evolve into more realistic scenarios, up to and including the likelihood of experiencing an installation failure on a piece of software. So this first example problem is called Carnival Dice Rolls. You're at a carnival and come across a person in a booth offering you a game of chance, as people in carnivals tend to do. Here's the setup. You pay $5 to roll 3 dice. Okay. If the sum of the dice rolls is greater than 12, you triple your money. If it's less than or equal to 12, you get nothing. So I like the upside. I like being able to triple the money, but that downside looks pretty down, right? Assuming all the dice are fair, should you bother to play this game? And what would change if the winning condition was the sum greater than or equal to 12? So pay attention to the setup here. The setup is we're rolling 3 dice at a time, and we're going to talk about how to set up our setups here, our simulations. One of the ways we can do this is by specifying dozens of thousands of trials. That's what that 10,000 is doing. We're going to play this game theoretically 10,000 times in Python. And if you wanted to do more, you do more. And the more trials you have, the more certain you can be about the answers that you arrive at. The number of columns here is the number of things per trial. So what are we doing? We're rolling 3 dice at a time. That's why the number of columns is 3. And just so you're not too freaked out by seeing this double assignment, n dice is pointing to n calls is pointing to the number 3. So both of those variables point to the number 3, just like n trials and n rows both point to 10,000 or whatever number you have there. This next little bit of code, np.random.choice, allows us to send in a list of numbers or strings or whatever data type and randomize them. What we don't have in this choice underneath is that this is an even likelihood of all of these outcomes. If we wanted to set the likelihood of each outcome differently, that would be an argument called P for probability, and that would take a list. Okay, so I don't want to get too ahead of myself. To recap, we're saying, hey NumPy, roll a dice And this second argument right here that's highlighted, notice that I am multiplying the number of trials by the number of dice. So 3 dice per trial, 10,000 trials, that's 30,000 dice we're rolling total. And this is taking a positional argument of the size. This is just a single scalar size. And then the reshape here allows us to make sure that each time we play this game is 1 row. So each row is 3 dice outcomes, and we have 10,000 times we play our game. The dot reshape allows us to reshape into number of things we're doing per trial time by the number of trials. So the setup for the game was we could triple our money, pay 5 and get 15 if we roll greater than 12. So let's sum this stuff up. Now, the sum argument by default, it's summing columns, but when we say, hey, sum axis 1, we're now summing rows. And so let's check this out. The sums by trial, the first row, 6 plus 4, 10, plus 5 is 15. That's the 15 right there. So that first trial, that's greater than 12. We paid $5 and we got back 15. The next trial, 6, 3, and 1. Well, those sum up to be 10. So that's bust. Okay. So what we can do if we want to visualize our outcome here, we totally could. Again, the code for this is in that viz module. And what we're looking at here is a histogram. We're looking at a frequency distribution of all the possible outcomes. 18 meaning we rolled 3 6s, the number 3 meaning we rolled 3 1s. And this is not a perfect normal curve because we don't have an infinite number of dice. We have 10,000, right? So there might be some minuscule differences. And with what's shaded right here, these are all of the outcomes where we win this carnival dice game. 13 and above, or above 12. So if we want to we've talked about getting an array of Booleans, and that array of Booleans is your keys to the castle with pandas. It's also the keys to your castle with summing things up or getting proportions of truths. So if our sums by each trial, for each one that's greater than 12, this will return true. And for each trial where those 3 dice sum to less than 12, we get false. That's where we're producing this wins array. And if we take this wins array and get the mean of it, we get the proportion. So we're winning about 26% of the time. We're winning in this game. And we don't know if this is worth it to play, because we still have to calculate in our win rate times the rate of winning, which is 26%, times that yield, times that $15 you get for winning. Then we have to calculate in the cost of the game. So expected winnings is the probability times the outcome. And we subtract the cost. And what we get is you are paying about $1 a game, $1.05 a game to play this one. Even if you win 25%, 26% of the time. Even if you're tripling what you put down on the table, 26% of the time. If we were to change, now if we change the win condition from our win condition being greater than 12 to being greater than or equal to 12, what that means is that all of the shading here of the win condition, if we say the win condition is 12 or more, we get this much more area of that distribution that makes for winning. I like the sound of that. I would love to go from paying $1 to playing a game to essentially walking away with 60 cents per game. And so let's check out the code here. We're saying wins are the number of sums by trial that are greater than or equal to 12. So wins is a Boolean array. If you have a Boolean array, you can get the mean of that Boolean array with .mean to tell you the proportion of truths. That gives us our winning rate, and we can take the winning rate, multiply that by the outcome for winning to get the expected winnings, take the expected winnings, subtract the cost, and our expected profit per trial, per game here is 58 cents. I'll tell you right now, I will play that game all day long. Twice on Sunday. Because in this different win condition, we're now walking away. Even if you hit a run of bad luck, over time, your average winnings are about 60 cents, 58 cents a game. And that's a lot better than losing $1 a game. Yeah, go ahead, Arsen.
Thank you. First, you get a haha for twice on Sunday. I've always had trouble with the determining the count when you have a Boolean array. It's right there where you were. Yeah. So you wrote the formula wins as type and then you calculated the mean with that mean. So if
okay.
Oh yeah, so if you could kind of like explain that a little bit again.
Yeah, I would be happy to. Let's build a simpler approach. If I have an array of true, false, and true, how many truths do I have? Just two, right? And how many of everything do I have? I have 3 of everything, right? And if I were to take the sum of the truths divided by the number of everything total, we would see 2 out of 3, wouldn't we? And
so maybe this is not the example that I was thinking about. I'll go through my notes and then I'll come back to you.
I think you already might. We don't have to like do a lot of other things. Just sum on its own will count up the truths for you.
Yeah.
And then the number of truths out of the number of total give you the proportion of truths. And you can skip that middleman by taking the mean of the array of Booleans, and you get the proportion of that array that's true.
Yeah, as I was looking at the code, like it's pretty simple, but I think the example that I was thinking about is much more complex than this. So I'll go through my notes and then probably during the session, I'll send it to you.
Yeah,
but thank you though.
Please do. I would be happy to get some eyes on what you're talking about.
Thanks.
Because this is a really nice to have it with an array of Booleans. And you may notice that being able to calculate our win rate, that's a magic tool for being able to determine our expected winnings. And if we can determine our expected winnings, subtract the cost, we have our expected win or loss that we walk away from the game with. Cool. Okay, so a little bit different of a scenario. Instead of rolling dice, let's take a look at this setup, no rest or relaxation. There is a 30% chance that Zach's son takes a nap on any given weekend day. Okay, so 30% chance of taking a nap on any given weekend day. What is the chance that he takes a nap at least one day this weekend? That's one computation we can do. And what's the probability that he doesn't nap at all? And I want to speak to our setup here. We're not dealing with a conditional probability. If there's a nap on Saturday, that doesn't impact if there's a nap on Sunday here, at least in this setup. Now, in reality, Zach's son may like to just nap all the time, or maybe he doesn't nap Sundays if he had a good nap Saturday. I don't know, not his parent, but it's important to note that the simulations that we're doing are assuming independence. That's very, very critical, assuming independence. Dependent probabilities are a different beast, and there's a lot to get into there, more than we have the time to in our 100 days of code up. But independent probabilities happen all the time. They happen in manufacturing all the time. They happen in social sciences all the time, right? So let's take a look at this setup. If we have a probability of something occurring, it's a really, really good idea to make a variable to hold that variable, to hold that value, right? So you're not banging around with just 0.3 in your head. The number of days is the same thing as the number of columns. That's going to be 2. This is assuming a 2-day weekend, right? Not a 3-day weekend, not a holiday. And what we're going to simulate is a certain number of weekends in a row. So each weekend we'll make 10 to the 5th. So that's 10,000 weekends to simulate. And we can crank this number up if we want. But we have 30% chance of something happening on any given day. 2 days in a row is what we're looking at. The 2 days in a row, that's kind of like the unit is a weekend. That's 2 individual days. Just like in that dice game, a game took 3 individual dice. It's important to get your head around this number of columns and what this is, how we're modeling things here. Okay. So we have 10,000 simulated weekends, and then the np.random, we talked about a number of those different random functions. Just np.random.random gives you a random number between 0 and 1. And this is a good way of generating probabilities. Because if 1 is 100% something happening, 0 is 0% chance of something happening, we can now generate probabilities to compare to that 30% likelihood of taking a nap. Jen? Yeah. Uh-huh.
Is it because we're doing Numpy random on random?
Yeah. So how to read this is Numpy is the library. Random is a module on that library that has a big honking list of different random functions. And then random itself is a method. Let's see, Numpy random. I'll show you what I mean. In the reference material, so we've been talking to Numpy through np.whatever, np.array, np.arange. .random is a whole other module inside of Numpy just for randomness, and it's got a lot. And this is just the tip of the iceberg for some of the random number generation. Yeah. How are we doing out there in TV land? Arsene, D'Angelo, Kate, Jules, Kayla, Cody, Lawrence, y'all doing all right? Ray? Cool.
Fantastic.
Awesome. Cool.
Good.
Outstanding. Okay, so now we're sitting on this this 2 by 10,000 array where each day is giving us a chance. And the probability of taking that nap, again, remember that that's 0.3, 30% chance of taking a nap on any given day. And so if we're trying to calculate the likelihood of a nap at least one day, there has to be at least one true. They could both be true to count for at least one day. And so each one of these pieces of data will compare to the probability, the known likelihood of Zach's son taking a nap on a given day. So if we can produce the array of Booleans, then you have the keys to the castle. I'm not kidding about this array of Boolean stuff, folks. It's really powerful with pandas because it gives you subsets. But when we're doing simulations like this, we can count wins or occurrences, right? So now we have a whole bunch of trues and falses together, but each row represents one weekend, one simulated weekend. Now, if we were to do axis equals 1, the sum axis equals 1 sums across the row. So this first row should be 0 because there's no truths. The second row has 1 because there's only one true. Third row has 1 because there's only one true. And if we were to look at the value counts, we would see 0, 1, and 2 here. Those are our options. Yeah, Fred.
Just as like a syntax point, it's axis 1, X, and then axis 2 is Y. Is that kind of how it works?
Yeah, go for it. Yeah, think about it that way is okay. We're summing across with the axis is 1, yeah, row wise. Let's see if we were to take a set of the naps, or let's keep it NumPy. How is naps not defined? I'll just take a set. Unhashable type. Get uniques. NumPy array. Oh, it's just unique. Why is this lies? Oh, because it's not off of the array, it's off of the NumPy library. Excuse me. So this is np.unique maps. There we go. Okay, so there's not a lot of unique values. We're either true or false. And if we take the np unique on naps.sum axis is 1, we only have a certain subset of options here. Let's talk about those options. We have no naps, a nap on Saturday or Sunday, either way. And then 2 means a nap on both days. Yeah, and that's 100,000. Yeah, you're totally correct, Arsene. So we can visualize our output here of those 3 likelihoods. It looks like almost half of the time, visually, there's no nap. And there's certainly quite a bit less 2 naps in a row. And so we can use this to answer our original question. So if we want to answer the original question, what is the probability that at least 1 nap is taken? Well, the highlighted bit of code in naps.sum axis 1 gives you that array of 0, 1, and 2. And if we are counting of that array, how many are greater than or equal to 1, then we can take the mean of that and we have a happy proportion, just a little bit over 50%. Now, what's the probability exactly no naps are taken? Well, that's we sum up all of the truths in our array of Booleans. And if the number of truths is exactly 0, it means nobody took a nap that weekend. And we can get the mean to produce that proportion. And that's 0.49. With respect to the rounding errors, if we summed up both of these, we would get exactly 1, because there's no other possible outcome. Either Zach's son had 0 naps, or he had 1 or more naps. There's no other possible outcome here. The big thing to remember, I'm going to walk y'all through one more simulation before we start in on the exercises. The big thing to remember here is if you have, if you're generating numbers, like with flipping dice or rolling flipping coins or rolling dice, the number of rows is the number of times you're performing the experiment. The number of items in your column are how many units of things per experiment, like 2 weekends and 2 days in a weekend, or 3 dice in a dice game and a dice hustle. So as long as you have that down, the difference between the number of objects per trial and the number of trials, you can crank up the number of trials, make it 1 million, make it 10 million, make your processor go freak out and go make coffee, right? The more trials you have, the closer you're going to get to a theoretical probability, okay? So if your number of trials is like 100, you're gonna have more error. But if it's like 10,000, you'll have less error. So let's look at one more setup here. And in this setup, we're going to do things with data frames, okay? What's the probability of getting at least 1 3 on 3 different independent dice rolls? Well, let's set this up. We're going to do 10 to the 5th number of rows. So that's number of simulations. We're rolling 3 dice at a time. That's why the number of dice rolled and the number of columns is 3. Our outcomes, if you can believe it, it's only a 6-sided die. We're not playing Dungeons and Dragons here, at least yet. And so of the possible outcomes, we have an even likelihood this is a fair die, and we're going to make that many rolls and get them into the right shape. And I'm not in love with how this is produced here. So I'm going to change it. Instead of this all being one-liner, I'm going to say number of 3s is let's take a look at what we have here. We have 0, 1, and 2 as our columns. And now I'm going to make a new column called number of 3s that will hold the result of applying a row-wise function that checks if the number of 3 is there. So let's take a look at this. Let's see, at least 1. Oh, not n 3s, but has at least 1 3. Let's name our things more carefully. So if there are no 3s, we get a false. If there is at least a 3, we get a true. If there's 3 3s, we still get 1 true. And what we can do with this is produce rolls dot has at least 3 dot mean to produce the proportion. Okay, so about 42% of the time, we're rolling at least 1 3 on 3 dice. And this number will change as if we crank up the number of dice per trial, right? What if we roll 10 dice at a time? Our likelihood's going to go up quite a bit, right? I don't know how much, but it roughly doubled. What if you're only rolling 1 die at a time? Well, that's about 1 in 6 chance. It's exactly 1 in 6 chance to roll at least 1 3. What about 2? Notice I'm changing the number of dice in my experiment about 30% of the time, and back to that original 3 dice, about 41, 42% of the time. Okay, so my advice here is, let's see, what might be new to y'all is axis equals 1 on summing. I think we've mentioned it, but y'all haven't like had to do it before. That's a little bit new. The idea of a Boolean array, that's not new, but this idea of the number of columns being the number of things per experiment, that's important too. I want you to really wrap your head around that. So if you're rolling 10 dice at a time, your number of columns is 10. Are we clear on that? I can say it like 7 more times, but I think y'all need to run into it and scratch your elbows or whatever and figure it out the fun way. Jen? Oh yeah, absolutely. Sorry. Inside of the curriculum, there's a one-liner, and I wasn't liking that one-liner. It wasn't crystal clear, so I broke it out into, I made the two-dimensional array, then I turned the two-dimensional array into a data frame. Then I made a new column on that data frame that held the result of counting if there was at least a 3 on that row.
Maybe I need to get this straight here, but
That's okay.
as I'm working with you, I'm actually getting different percentages. Is that just based on my random numbers?
If we ran the same random seed and ran everything in order top to bottom, it would be identical, but I've run a couple of my cells a couple of times. So I'm probably already off of yours. Yeah.
This might be a bigger question than we can talk about right now.
Okay.
Is it really possible for this to generate random numbers?
No. No.
Right, that's similar. Okay, so
The question was, is it really possible for this, meaning Numpy or pandas, a deterministic system to produce randomness? The short answer is no, but we can, it looks pretty random.
there's a really cool number file video about that specifically. It shows the repeat patterns you do it over time, but it's like millions of numbers. So it's essentially random
For the scope of a human's life.
Right.
Yeah, there's randomness is a big deal in security as well, and generating like if you tell me that your system is generating a random number for people who are authorized to have it, if I could figure out the means by which you generate those random numbers, then it's mine, right? I'm trying to remember who did this. I think it was Cloudflare. So Cloudflare hosts a bunch of content delivery networks. They make the internet work faster, better, right? They've got a wall of lava lamps, like not like a little wall, like a huge wall, like a 20-foot by 20-foot wall of lava lamps. And they'll take pictures of this because the physical systems generate more randomness. And then they'll use that as their seed to a deterministic system, like a computer program. Yeah, yeah, really wild. Jen, did this answer your question on the proportion, or was it just the noticing we were getting different numbers?
It's just noticing.
Okay. It wasn't about the code.
Well, no, I just made sure that I didn't look right because I noticed a different number.
Cool. So Jemison, Monte Carlo methods in Python. Monte Carlo methods in Python, Jemison. Right? Nice to introduce y'all. We'll take a break because we've been at it for about an hour here. These exercises, hey, you guessed it, you're going to make a brand new repo called statistics exercises. It will be a sibling in your code up data science to everything else you've been doing. And we've got a boatload of questions. And if you're into funny sided dice, the bonus exercises exist for my folks who like funny sided dice. Get after it, take a break, get after it, and let us know where we can be of assistance for y'all.